Hello, everyone. In this lecture, we're going to continue our discussion on queuing theory. So today we're going to look at the burst-dense queues with infinite capacity and finite capacity. So in the previous lecture, we talked about the queuing system in general, the introduction, and also the Little's law. So today's lecture, we focus on the burst-dense queues with finite capacity. So in the next lecture, we're going to talk about network models of queues. Okay, and we're also going to have a look at an additional lecture, look at a case study on how to develop queuing models for healthcare system analysis. Okay, so this page. Let's first have a look at the burst-dense queues with infinite capacity. So here you see this is M1, and we don't specify the capacity, so we assume it's infinite capacity. So M is the arrival process, exponential, memoryless. This M is the service time, exponential, and memoryless. We have one single server. So pretty much it's like this, this diagram. So this is arrival rate, and we increase, can go to infinity, the queue. And then we can also go back with the service time. So based on the rate equality principle, so for a particular state, rate at which the process leaves equals to the rate at which it enters. Okay, so for a particular state, we have two rates entering. Okay, for the first one, we have lambda p0 equals to mu p1. If it is n, then we have lambda plus mu, okay, pn, lambda plus mu pn, this n, state n, go out, lambda, go in. So the rate at which the process lives is lambda plus mu, this lambda plus mu, pn, and the enters will be lambda pn minus 1 and the mu pn plus 1. So the enter, rate at which it enters. So if we write all the equations for all the n, we will have a series of balanced equations. If we move this mu to the other side, we will have p1 equals to lambda over mu p0, and a pn plus 1 equals to lambda over mu pn plus pn minus lambda over mu pn minus 1. Okay, for all the n greater than or equals to 1. Now, we know if we add all the pn together from 0 to infinity, this way equals to 1. But all the pn, you see, this will equals to, if we transfer this set of balanced equation, it will become this form. So let's make rho equals to lambda over mu. So this is burst-dense ratio. So P0 equals to P0. P1 equals to rho, okay, lambda over mu, okay, lambda over mu P0. And a P2 will equals to lambda over mu square P0. And then Pn equals to lambda over mu n P0. So if we put a rho in, so we will have rho P0, rho square P0, that's P2, rho cube P0 equals to P3, and rho n P0 equals to Pn. So that's a relationship between all the P1 to Pn and the P0. They're connected through the rho. Okay, now, if we put it in this way, we add all of them together equals to 1, we can solve for P0. P0 basically is 1 minus rho. Okay, and then Pn equals to rho n, 1 minus rho. So rho is the burst-dense ratio, lambda over mu. So lambda over mu should be less than 1. That means this will make sure this process, this is stable, because the arrival rate is less than service rate. Why? We have to make sure this is less than 1. Let's have a look at. So the condition of stability, lambda over mu, must be less than 1. So lambda less than mu. So if lambda less than mu, the arrival rate is less than service rate. Okay, the system is able to handle the load. The Q does not build up to infinity. So limiting probability exists. This is what I call stable. If lambda greater than mu, the system is unable to handle the load. The Q builds up to infinity. So this is very unstable. So lambda, if lambda is greater than mu, so this summation, this is more than 1, right? The n goes to infinity. This has to go to infinity. Then Pn goes to 0. Why is this? Because if lambda over mu power n goes to infinity, P0 will equals to move this summation to this side, 1 over infinity. P0 will be 0. Then all the Pn should be 0. Pn goes to 0. Okay, then this will be, you are not going to, the probability, Pn denotes you are going to stay, the long run probability of fraction of time you stay in a particular state. And basically it's transient. You're not going to have a probability to stay in that time, in the particular state. So what about lambda equals to mu? The Q is still unstable because the effect of randomness, no leftover capacity to absorb the random build-ups. So we have to make sure lambda is less than mu. So this is also one condition that this summation this series can give us converge and become 1 minus lambda mu. Okay. Okay. Now, if for the MM1Q, what is the probability that a server is idle, server idleness? That is P0. The server is idle because there's nobody, the fraction of time there's nobody in the system. So P0 equals to 1 minus rho, so 1 minus lambda over mu. So it's over here, P0. And the probability that server is busy is 1 minus P0 equals to lambda over mu. So this is rho. Expected number in the system. So that's n, Pn, the expectation. So we know Pn equals to rho n, so lambda over mu, because rho equals to lambda over mu. Rho n, 1 minus rho. So we do the summation together, we will be able to get, this will be lambda over mu minus lambda. Based on the Little's law, we have expected number in the system, and then expected time that spent in the system. Okay, expected waiting time in the system. So W equals to L over lambda. Lambda is the arrival rate. So this is 1 over mu minus lambda. So WQ, so what is the average waiting time in the queue? Because this is a waiting time in the system, so W minus the service time. So 1 over mu minus lambda minus 1 over mu, this will become the waiting time in the queue. If we know the waiting time in the queue based on the Little's law, we will be able to get the average number of customers waiting in the queue. Okay, so this is lambda WQ, and we times down lambda. Lambda square over mu minus lambda. So now we have finished the MM1Q. What if we have S servers? Still infinite capacity, but we have S servers. So what's the difference? Previously, we only have mu here, right? But now you have S servers. Whenever you have less than S customers, okay? For example, you have 2 customers. Then both customers will get into the server because you have S servers, if S greater than 2, okay? Then the service rate, they will be 2 mu. If you have 3 customers, if S greater than 3, then the service rate is 3 mu. So until you reach S customers, then S servers serve these S customers. The service rate in total will be S mu. And when you reach S plus 1 customers, you can only serve S customers, still S mu. The 1 is actually waiting in the queue, okay? So now you have S mu, they are constant. So an MMSQ is stable if and only if lambda less than S mu. Okay. So the arrival rate is less than the service rate in general, okay, in every state, because lambda arrival rate is less than the service rate, so that the system able to handle the load. Now the service rate is S mu. So for a particular state, lambda I equals to lambda, and the mu I equals to the minimum of S and I mu times mu. So if I is less than S, then this is I mu. If I greater than S, this will be minimum, right? So it will become S mu, so like this. Now let's define rho equals to, previously we have rho equals to lambda over mu, right? Because we have constant arrival rate and the constant, that's lambda, and the service rate mu, the same. Now you have S mu, so let's define rho equals to lambda over S mu. Then rho I will equals to lambda 0, lambda 1 to lambda I minus 1, and divided by mu 1, mu 2 to mu I. Let's define rho I in this way. Okay, rho defined as this ratio, but rho I is the lambda over mu, okay? Lambda is a series of lambda. Now, this rho I, because we define it in this way, right? So rho I, when the I is less than or equals to S minus 1, okay? So this will become 1 because it will equals to lambda over mu, lambda over 2 mu, lambda over I mu, right? So it will become I, you see, I factorial, lambda over mu, then I power I. When I greater than or equals to S, this will be very interesting because now you see here, why we have S power S and S factorial? Because you see here, for this equation, you can rewrite it as lambda over S mu, then you put an S here. Lambda over 2S mu, you put an S here. Okay, so you have S power S. So this is exactly the same as this part when you reach S. But when you are over S, then you just multiply by lambda over S mu, lambda over S mu, right? Okay. So what you have here is this part is S power S over S factorial. Okay. Because up to S, you have 1, 2, 3, 4, to up to S. So this is S factorial. And then after you reach S, you will multiply by lambda over S mu, lambda over S mu. So this will be rho I. Okay. So you just have rho. And so what you have here is, this is lambda over S mu, right? Then S squared. And then the lambda over S mu power I. So this is lambda over mu power I. This is lambda over S mu power I. If you understand this rho equals to lambda over S mu, you will understand why we have S power S and S factorial here. Basically, if you look this closely, this is for I equals to S. Then I equals to S plus 1, you just add another lambda over S mu. Okay. Now, we know that the summation of rho I, we need to calculate the summation of rho I, because only by knowing the summation of rho I, because here you see the summation of rho I. Okay, P0 equals to 1 over summation of rho I. Okay, this is rho. So let's first calculate the summation of all the rho I. Okay, so equals to 0 to S minus 1. So this will be rho I. And from S to infinity, it will become, this rho I will be a different rho I. So you will have S power S, S factorial. Then you will have rho power S divided by 1 minus rho. This rho, what is this rho? This rho is lambda over S mu. Again, pay attention. This is lambda over S mu, not lambda over mu. Okay. So if you put this rho I, because less than S minus 1, this will become this, right? You can put this over here. And this part, you can sum to the infinity. You got a rho S over 1 minus rho, because it starts from rho S. Okay. So now if you take the inverse minus 1, you got a P0. And a Pi equals to P0 rho I P0, the same. Okay, so now you calculate the P0 to Pi based on this equation. And this rho I is defined in this way. This rho is actually this lambda over S mu. Okay, so a critical part to understand this equation is actually you have S servers. So make sure you pay attention to the transition from S mu. When it reaches S, then S plus 1. So S mu, they are constant. Okay. And also note this equation. This equation is very critical for us to understand how to simplify the equation into this ratio to represent by using this ratio. Okay, now we got a P0 and the Pi, all the Pi. Now, what's probability of waiting? Okay, so there are S servers. If it is more than S, there are more than S customers, then we won't have people waiting. Okay. So the summation is from S to infinity. And now, so if there are S customers, they are all in the server. When the next one come, and it will wait. Okay. So the summation is actually Pi equals to P0 rho see rho I, no, previous one. Rho I, because it's greater than S, so rho I will become, this rho I is the index. See, this rho I. This is rho is a constant, S lambda over S mu, and this is power. So we put this into here, P0 S power S factorial rho I. You see here, right? So P0. Now, if we calculate this part, okay, let's put this part over here, and then let's, because this part is a constant, right? It doesn't have I, so we put it out. Then we extract a rho S out. So summation will go from rho I minus S, go from S. Now let's change the index. You see, this is I minus S, right? If we change the index, this will become rho I and start from 0. So this will become PS over 1 minus rho. So this is an interesting result on probability of waiting. Now, what's the expected number in the system? Similar as before, this is I, Pi. Now, we have the P here, P0, Pi, all the P's. Now let's put it in. We will be able to get lambda over mu plus PS, okay? PS rho over 1 minus rho square. Now, the expected waiting time, we're going to calculate based on the Little's law, that is W equals to L over lambda. So divided by lambda, then because this rho is actually lambda over S mu. So if we divide by 1 lambda, then this will become 1 over S mu. So this is the expected waiting time, average waiting time. This is the average number in the system, average waiting time in the system. This is the probability of waiting. Now, based on the results, let's have a look at an example, okay? Suppose USPS office, they want to realize the goal that no customer will have to wait more than 5 minutes in line in the post office, okay? Now, no customers have to wait more than 5 minutes. Now, the question is, how many service windows to keep open so that the mean queuing time, excluding the service time, is less than 5 minutes? So suppose the arrival rate is lambda, service rate is mu. So now the queuing time, excluding the service time. So previously, this is expected waiting time in the system, including the service time. Okay. If we minus the service time, okay, it will become only this part left. So this will be 1 over S mu PS over 1 minus rho square. Now, this is a waiting time have to be less than 5 minutes. We want we want to find out how many service windows, how many servers should we S. Okay. Now, average service time for one server is like a 3.8 minutes. So the mu is 60 over 3.8 is 15.7895 per hour. So the arrival rate is 47.2 per hour. In order for the queue to be stable, lambda must be less than S mu. Okay, lambda over S mu has to be less than 1. That means arrival rate has to be greater than the arrival rate has to be less than the service rate, S mu. Now, if S equals to 1, 2, so 1 times mu or 2 times mu, 2 times mu is about 30 or 32, right? So this is obviously less than lambda. So the Q is unstable for S equals to 1 and 2. So we're not going to consider. Let's calculate S equals to 3. Let's put S in, and mu and lambda and the PS, they are all in the system. After we do some calculations, this will equals to 353 minutes. That's a long waiting time if you have 3 windows only. If S equals to 4, if you have 4 service windows, then the average waiting time in the queue will be 0.0316 hours. That is 1.8936 minutes. Obviously, we realize our goal, and the waiting time is less than 5 minutes. Now, so far we had a look at MM1Q, MMSQ. Now let's have a look at MM infinity Q. So in steady state, the number of customers in MM infinity Q, okay, is a Poisson random variable with parameter lambda over mu. Okay. Now, you see here, when we calculate this part, you see this is infinity, right? So previously we calculate P0. P0 equals to this. If we have S goes to infinity. As S goes to infinity, this will become, if you do some derivation, this actually equals to exponential lambda over mu. But we know that Pi actually equals to P0. P0 is exponential lambda over mu. This actually, rho I, what is rho I? Rho I is lambda over mu I over I square. Okay. Now, let's have a look at this. You see here, I square lambda over mu I. Because this S goes to infinity, right? So we don't have this part, S goes to infinity, so we only have this term. So this will become exponential minus lambda over mu, then we have lambda over mu I over I squared. So this part will become a Poisson random variable with parameter lambda over mu. Okay. So if we look at the average length, so this is the parameter, right? So average is actually the expectation of a Poisson random variable is lambda over mu. And then waiting time in the system will be L over lambda. So this become 1 over mu. Basically, it's just the service time because you have infinite servers. So the limiting distribution of MM infinity Q Pi will become, actually, this is as K goes to infinity. This K goes to infinity. This K server goes to infinity. It will actually equals to MM infinity Q. This is a very interesting result. Now, let's have a look at an example of the library, okay? Now, users arrive at a rate of 200 per hour. Each user stays for an average of 24 minutes, that is IID, exponential distributed. How many users in the library on average? So library is very big, right? Let's assume the library have infinite servers, and people come and study, and then they can leave, and they get a service right away, right? So lambda equals 200, and mu equals to like 60 over 24 per hour. We need to convert the unit to be the same, to be consistent. So how many users in the library? This is lambda over mu. So lambda over mu, 200 multiplied by 24 divided by 60. So this is about 80 customers, 80 users in the library on average. Okay, so far we talk about the infinite capacity, okay? Now let's suppose we add a capacity K over there, okay? So this will be finite capacity. So still the same state, rate at which the process enters, leaves a state, equals to the rate at which it enters the state. This is balanced. So let's assume constant now because we only have one server, right? The lambda mu. Now, this actually comes to K, only comes to K minus 1. When it comes to K, you will have mu, you will only have leave, right? And then you enter mu pk equals to lambda pk minus 1. So based on this set of balance equation, if we move this mu to the other side, we still got rho equals to lambda over mu. Rho equals to this lambda over mu. So we will be able to get a pi equals to rho pi minus 1 equals to lambda over mu square pi minus 2 to lambda over mu I p0. Okay. So this set of equation is still the same as MM1. Let's go to MM1. You see here, P1 equals to lambda over mu P0, right? P2. But this n goes to infinity, right? This n can go to infinity. You see, n can go to infinity. But now you add a cap, K. If you add a cap, the capacity K, now it only comes to K. Now, if you sum all the P0 to P1, P2 to Pk, they equals to 1. But you add all of them together. This is P0. Sum all the rho I together. Now this series has a cap, does not go to infinity. If it goes to infinity, it will become 1 over 1 minus rho. If it goes only to K, it will become 1 minus lambda over rho K plus 1 over 1 minus lambda over mu. This is rho. So P0, what will be P0? P0 will equals to, let's move this to the top, the 1 minus rho over that rho equals to lambda over mu. So this will be 1 minus rho divided by 1 minus rho K plus 1. And the Pi equals to this P0 rho I. Okay, so we put this over here. If rho doesn't equal to 1, it will equals to, because rho power 0 equals to 1, right? So Pi it will equals to this equation. If rho equals to 1, lambda equals to mu, then the probability to be in each state is equal, right? 1 over K plus 1. Now let's have a look at the server idleness. Okay, for the MM1K, so now we have add a cap, the capacity. Okay, so the long run fraction of time the server is idle will equals to P0. Okay, 1 minus rho K plus 1. So this is P0. Blocking probability long run fraction time the server is full, that is Pk. Pk is 1 minus rho K plus 1, rho K, so it's actually K. Pass time, we have Poisson arrivals. An equals to Pn. Poisson arrivals see the time average. Okay. So what is the entering customer? What about the entering customer? The probability that entering customers sees I customer in the system ahead of him. What is pi I? Star. Okay, an entering customer, see I customers in the system ahead of him. Okay, so probability customer sees I in the system. Entering customer sees I in the system, which actually equals to probability arrivals see I and arrivals enter, given the arrivals enter, divided by probability arrivals enter. So probability arrivals enter is 1 minus pk. Okay, it's not blocked. And this is the union. Okay, arrival sees I in the system and arrival enters sees I in the system. That's pi. So this union is not this is union with this. It will become just a arrival sees I pi. So this is a probability that an entering customer sees I customers in the system ahead of him. It has to be given the condition on the arrival enters. So this is 1 minus pk. So why I less than or equals to k minus 1? Because if I equals to k, the customer will want to enter. So here the probability is an entering customer. What about the expected system, expected number of customers in the system? So this is IPI. Now you see we have a cap k. So if rho equals to 1, this is 1 over k plus 1 summation I. So this will become k plus 1 divided by 2. So k plus 1 canceled. So this is k over 2. If rho does not equals to 1, definitely it should be less than 1, right? So then L equals to I pi. So it will become 1 minus rho, 1 minus rho k plus 1. Move this part out, then I rho I. So this will become, now it will become this equation. So this is the expected number of customer in the system. So what is the expected waiting time for the arrivals? So W equals to L over lambda. This is Little's law. Arrival, but the arrival actually can spend no time in the system if he finds the system is full. So this is for arrivals. Now, suppose the customer enters. So expect time, waiting time for the entries. So arrival rate of entering customer. Entering customer, this is entering customer, arrival rate. So it's lambda times probability that arriving customer enters. So this is lambda times 1 minus pk. Okay, so this will be the rate of entering customers. This is the rate of arrival rate of all customers. This is only for entering customers. Now, let's use this L. Okay, L divided by lambda E, we will be able to get the expected waiting time for the entering customers. Now let's have a look at an example. Suppose we have M15Q and lambda equals to 10, mu equals to 15. What's the probability of system to be full? And this P5. How to calculate the P5? P5 is here, right? P5. You just put this as 5. And 5 plus 1, 6. And then we have lambda over rho, lambda over mu equals to rho, right? So you can calculate the P5. So expected waiting time of entering customer will equals to this WE. You have PK right here, right? So you have L, and then you will also have lambda. So this L is right here. You also have lambda equals to 10. So this will become 8.97 minutes. Now let's have a look at another example on MM1KQ. Suppose it costs CU dollars, CMU dollars, okay, CMU per hour to provide service at a rate mu. Because if you want to provide service, you have to pay those servers, okay? But if they do it at rate mu, so you have to pay CMU dollars. A gross profit of $8 for each customer served, and the capacity is K. Now, which service rate maximizes the profit? You see, profit per hour is actually equals to still the rho equals lambda over mu. Lambda, this is the entering customer, okay? Entering customer, the rate of arriving rate of entering customer, lambda 1 minus pk. So for entering customer, and you are going to, this is a rate, you are going to have a gross profit A. So this is a profit at this rate. And it costs C mu per hour, okay? So this is per hour that you get a profit from the customer. So if you put a pk into this equation, you will get lambda 1 minus rho, 1 minus rho k plus 1 rho k, A minus C mu. Let's put mu, lambda of mu into this equation. You will solve for this, okay? Now it's very interesting, right? So it will become, it will become you see here. So if you multiply by this and this, so this will become rho k minus rho k plus 1. So this is 1 minus rho k plus 1. So if you put it here, this is rho k plus 1, rho k plus 1 canceled. So this will become 1 minus rho k. So this is where this from. Now, suppose we have n equals to 2, okay? N equals to 2. That means k equals to 2. So here, this is the capacity, okay? Capacity is 2. Lambda equals to 1. A equals to 10. C equals to 1. Now let's put it in. This is 1. This lambda equals to 1. And A equals to 10. 10. Lambda equals to 1. And the K, capital K, equals to 2. So this is capacity. Now, if we put them in, we will be able to get the equation for this profit per hour is actually a function of mu. Now, how to get the minimum or maximum? This is a concave function, actually. Which service rate maximizes the profit? So we're going to take the derivative and do the differentiation, and then set this equal to 0, solve it for mu optimal. This will give you the best optimal service rate. Now, previously we talked about MM1K Q. Now let's have a look at MMSK. So now you have S servers. So similar to before, now you have minimal IS mu. Okay. So S sometimes should be less than K. Okay. So I is less than K, greater than 0. This is mu I, this is lambda I. Let's make this rho. Now we change this rho to be defined as lambda over S mu. Obviously, lambda over S mu needs to be less than 1 for the system to be stable. And similar to before, we can get the Pi equals to P0 rho I, and rho I is defined in this way. Okay, now you see here, the difference is this is capped at K. If you go to the previous one, this is capped at infinity, right? It goes to infinity I. Now you have a cap that is goes to K. And then if you do the summation, you sum all the rho I together to K, and this is your derivation, then you will be able to get this part. Okay, so P0 equals to 1 over the summation from 1 to K rho I. So this will equals to this, actually this inverse. Inverse. Once you get a P0, you get all the PIs. Okay. Now, let's have a look at an example. Did I skip any slides? Oh, this is 14, this is 15. So suppose we have a call center. We have MMSK. Okay. Now the server number of servers is less than the capacity. Okay. So MM610. and lambda equals to 60 per hour, the arrival rate. Service rate is 10 per hour per server. Find the limiting distribution. Because we know this is 610, and using this equation, we know lambda mu, and we know S is 6, right? K is 10. So we can solve for this. We got a P0. P0 equals to 0.002. Then we times rho I. We got all the rho I. And we will be able to get the limiting distribution. So expected number of calls on hold, because you only have 6 servers. When it comes to 7, the 6 are on service. When the 7 comes, 7 to 10, they will be on hold until somebody finishes service. They will be able to enter the service. So this will become a number of calls on hold, because I equals to, if there are 7 customers, you will have 6 on service and 1 in hold. So that's I minus 6 times P7, okay? It's 1 times P7 and 2 times P2. And then it will become 1.2862. So what a fraction of the calls are lost? That is P10, okay, P power K. It's about 12.86%. Now, we talk about SK. Now, suppose the server actually approach, the number of servers is same as the number of capacity. So S equals to K. So this is called a loss system, okay? Any customer who cannot enter service immediately upon arrival is lost, okay? So if the customer find, okay, now I enter the server, that's enter the queue, and there is 1 server available, then I enter the service, because K equals to the number of server equals to number of capacity. Now, in this case, the limiting distribution will become like this actually rho I divided by, okay, 1 over J from 0 to K. This is actually P0 rho I. And rho I actually equals to lambda over mu I over I squared. And rho 0 equals to 1. If we look at this is actually a truncated, okay? This is a truncated Poisson random variable, and I less than K greater than 0, truncated at K, okay? So probability, we have Y equals to I, and given that Y less than K, this is the truncated at K, equals to this, you see, joint probability, Y equals to I, Y less than K. This actually is Y equals to I, because I is less than K. And then given that Y less than or equal to K. So because this is a Poisson random variable, right, Y, and truncated at K, so Y equals to I is actually equals to exponential lambda over mu I divided by I factorial. And here, Y less than K, this is summation from 0 to K, and then for all the J. If we calculate this will become lambda over mu I factorial. And this is actually, this part is this part. This part is this part, rho I. So that's why this limiting distribution is actually the truncated Poisson random variable. And it actually equals to PI. Make sense? So this is actually the proof. This is a truncated Poisson random variable, truncated at K. This actually, if we put this Poisson distribution into this equation, we will be able to get this actually equals to rho I right here. So that's why the MMKK, the loss system, the PI limiting distribution is actually the distribution of a truncated at K Poisson random variable. So far, we finished the burst desk queues with infinite capacity, MM1, MMS, MM infinity. Then we talk about burst desk queues at a finite capacity, MM1K, MMSK, MMKK. Now let's have a look at an example. Okay. A shoe shine shop. Consider a shoe shine shop consisting of 2 chairs. This is a shoe shine shop with 2 chairs. Suppose that an entering customer first go to chair 1. Okay. When his work is completed in chair 1, he will go either to chair 2 if that chair is empty, or else. So if this chair is not empty, has a 1 customer over here, he has to wait. And then until chair 2 becomes empty, he will enter chair 2. Okay. Suppose a potential customer will enter the shop as long as chair 1 is empty. As for instance, a potential customer might enter even if there is a customer in chair 2. Okay. So the service, you have to go through like chair 1, chair 2, then you exit. If we suppose the potential customer arrive in accordance with a Poisson process at a rate lambda, and then service time for the 2 chairs are independent, have respect exponential rate mu1 and mu2. Then now, for this example, we have to answer these 3 questions. What a proportion of potential customers enter the system? What is the mean number of customers in the system? What is the average amount of time that an entering customer spends in the system? Okay, we have to answer these 3 questions. Now let's see how to do it. So previously, when we define the state of system, we often use the number of customers. But here we cannot use number of customers. We have to have a more detailed state space because we have 2 chairs. Okay. Let's use 0, 0 to denote no customer in the shop. And 1, 0, 1 customer in the chair 1. 0, 1, 1 customer in chair 2. 1, 1, 2 customers, both are presently being served. And the B1 means 2 customers, first chair complete his work and is waiting to be served in chair 2. You see here, if it is 0, 0, then we have a rate lambda to have 1 customer come and serve in chair 1. And then we can have 1, 0, right? It can move to 0, 1. 0, 1 means this customer finished service in chair 1, moves to chair 2. If it moves to chair 2 and it have mu2 to exit, because finish chair 2 and then exit, or it can has a rate lambda. Okay, if lambda comes, then it will become 1, 1. If an arrival comes in chair 1 and the chair 2 still have 1 customer here. Then if we have both customers, okay, are presently being served, now mu2 can finish service and then become 1, 0. Okay. And all mu1, the chair 1 finish and then become B1 because the first one is blocked. Okay, and waited to be served in chair 2. And if first customer, the chair 1 is blocked and chair 2 is being served, and then if chair 2 finish at a rate of mu2, then it would become 0, 1 because this blocked customer moved to the chair 2. So this is a transition diagram among the state. Okay, among those states. Now, we know that we have rate equality. Now let's derive the balance equation. In the balance equation, the state, for every state, rate at that the process leaves and the rate that the process enters have to equal. So lambda P00, so lambda P00 leaves equals to mu2 P01. Okay. If for 1, 0, that is mu1 for 1, 0, let's go to 1, 0. 1, 0 leaves is mu1 P10 and enters is lambda P00 plus mu2 P11. So mu2 P11. And same we can derive for all states. This is our balance equation. We also know that the probability in all the states 0, 0, 1, 0, 0, 1, 1, 1, or B1, it should be summed to 1. Okay, now we were asked 3 questions. We need to solve this set of equation. If we know lambda mu1, mu2, and we will be able to solve this set of balanced equation. Now, the proportion of customer entering the system. So if P00, right, it enters. P01, first chair is empty, it enters. So average number of customers in the system, average number is actually L equals to 1 times P01, 1 times P10 plus 2 P11 plus PB1. So this is average number of customers. Average amount of time entering customer spends. Okay. So the arrival rate of entering customers. So this is a proportion enter, right? So the total arrival rate times the proportion enters. This is the arrival rate of entering customers. So this is the average number of customers in the system. So L over lambda A, this is the average amount of time entering customer spends in the system. So this is how we solve the balance equation and answer the 3 questions for the shoe shine shop. Now, through these lectures, we actually discussed the burst SQs, burst with infinite capacity and finite capacity. Okay. Now, this concludes today's lecture. In the next lecture, we are going to look at a case study on Q. We're going to look at the network of Q first, and then we're going to look at the case study. So this is the end. See you in the next lecture.